Look at a car's speedometer. The needle says 60 right now, this instant, not 60 miles averaged over the next hour, 60 exactly now. But speed is distance divided by time, and an instant has almost no time to it at all. So how can there be a speed at a single frozen moment? The answer runs deeper than you'd expect. To see it, start somewhere simpler, with a plain, straight line on a graph. Put distance up the side and time along the bottom. A car moving at a steady speed traces a straight line, and the steeper that line climbs, the faster the car is going. We measure the steepness as rise over run, how far the line climbs, divided by how far it moves across. That ratio is the slope, and here, the slope simply is the speed. On a straight line, it's easy, because the steepness never changes. Pick any 2 points you like, and rise over run gives you the same answer every single time. But real motion rarely holds a straight line. Speed up, ease off, and the graph bends into a curve. So what is the slope at one point on a curve? Here, the steepness keeps changing, so we sneak up on it. Take your point, then a second point a little way along, and draw the straight line joining them. That line is called a secant, and its slope is the average speed across the gap between them. Now slide the second point in toward the first. The gap shrinks, the secant pivots, and it settles onto a single line that just grazes the curve at your point, the tangent. Its slope is the speed at that one instant. Write it as a fraction. The change in height, f of x plus h minus f of x, all divided by h, the tiny step across. As h shrinks towards 0, that fraction closes in on the tangent slope. The whole idea rests on a limit. And there's no need to redo that work point by point. Do it for every x at once, and the slopes themselves form a brand new function, the derivative, written f prime of x. Feed it a position, and it hands back exactly how steep the original curve is right there. That's what makes it powerful. Wherever a curve peaks or bottoms out, it levels off for an instant, so its slope there is 0. Set f prime of x equal to 0, solve, and you found the maxima and minima, the highest, the lowest, the best, and the worst. From a needle reading 60 to a function that reads the steepness of any curve, the derivative is just the slope at a single point, made exact by letting the gap shrink to nothing. The speed at an instant finally pinned down.